All right, good morning, everyone. I hope you're doing well this morning. I want to apologize for not being able to attend our class synchronously on Monday. I had some emergency with my car and I had a flat tire and got strangled in the middle of nowhere, and I couldn't get to my office, so I had to get it repaired. All right, I hope that you had a chance to look at your the recorded lecture I did for Monday. The main new concept we had talked about on Monday's class was to calculate the pressure underneath some liquid. So if you're looking at a liquid and if you're right at the surface of the liquid, then you're looking at atmosphere pressure. Okay, so the 1 atmosphere pressure is about 100 Pascal. 1 Pascal is 1 Newton per meter squared. And if you use a different unit, for example, if you use pounds per inch square, then 1 atmosphere pressure is 14.7 PSI. So that's just, we use different units when it's convenient to use one and the other. But if you're underneath a surface, then you need to add the extra pressure that is related to the weight of the liquid. So for example, if you have some water, okay, so right here you have just the atmosphere pressure. But if you add a distance h below the surface of the water, and the water at this point will be P naught plus rho times G times H. Rho would be, if it's water, is the density of the water. If this is some other liquid, it will be density of that liquid. There's other ways to represent how big 1 atmosphere pressure is. For example, a lot of times people are looking at mercury barometer. The idea is how high of a mercury column that the atmosphere pressure could support. So we could measure this by doing such a thing. So for example, we can fill a tube with mercury upside down in the bucket of mercury. Now, if you fill it upside down, then some of the mercury will run out, and eventually it's going to be at stable equilibrium, leaving this top to be a vacuum space. Okay, so there was no air in it because at the beginning you fill everything up with mercury, so there is no air that was in the tube. So you can see that, well, how come these mercury column did not all fall out? That's because you have the atmosphere pressure. We're saying that the pressure is coming from all different directions, right? So the atmosphere pressure coming in this way, atmosphere pressure pushing in this way. So they are supporting the weight of this entire mercury column. So we can calculate how much height that is by setting up these two pressure to be equal, right? Because the pressure from the column of the mercury is equal to the atmosphere pressure. And then at that point, your mercury is stable, is at the static equilibrium. All right, so if these two pressures are equal, then you can, this is another way to tell people how much pressure you're looking at, because 1 atmosphere pressure is equivalent to the density of the mercury times G times whatever height of that column it can support. And that turned out to be 760 millimeters of mercury that 1 atmosphere pressure could support. If you do this experiment somewhere else where you don't have 1 atmosphere pressure, let's say if you go to a high mountain where the pressure is much smaller than at the sea level, then you're expecting to support a much shorter column of mercury, right? But so sometimes people say 1 ATM would just be a 760 millimeters of mercury, and that's also equivalent of saying 14.7 pound per inch squared PSI. Now, some of these I'm sure that you have encountered in daily lives. For example, when you measure your blood pressure, a lot of times they're using the millimeter mercury as the unit. So you know what it means and you know how to convert it if you need to. By PSI, in terms of filling up your tires, you hear them using the units of PSI. So all of these are just different units to talk about atmosphere pressure, how much pressure we're talking about. All right. So you can see the atmosphere pressure in this case pushes. The fact this mercury column did not fall out is not because this vacuum right here tried to suck it up. It's because the atmosphere pressure from the outside is push it in. Okay, so that is a very important thing. We will look at a question related to that later. So if you, instead of using mercury, if you create such a device of water, fill it with water, and this is vacuum, of course, and the height of the water that you could support also changes. Okay, the height of the water would be 10 meters, which is about 33 feet for the one normal atmosphere pressure. Okay, because the water's density is so much smaller than the density of the mercury. As a result of that, you can support a higher height of the water than you can support mercury. You can switch out that to any other kind of liquid, but oftentimes people use mercury as a way to measure how much pressure there is. Now let's look at a question. So you can drink water through a straw. You're trying to drink water through a straw, and imagine the straw is super long, and you're trying to stand up on the platform that's 40 feet above a glass of water and drink from there. Okay. So do you think that you will be able to drink the water from that straw, or maybe not? So I'm gonna go ahead and let you vote on this. So notice that two choices are choice A and B. Okay, I'm seeing some C answers, so I assume that you meant B. There's no C answer. All right, let's go for 10 more seconds. All right, any last minute vote? All right, so I'm going to end the poll. Let's take a look. Okay, so it looks like quite a significant percent of choices say yes, if I suck the straw hard enough, I could get the water up high. Or B, no matter how hard that you try to drink, you're not going to get that water up that high. So anybody would like to be able to explain either of those choices? Reasoning for either of those choices?
Well, so personally, I'm not 100% sure why, but I think you can't, just because if we can see right now on the slide, the HO water is 33 feet, and 33 feet is it's great. It's less than 40 feet, and it doesn't matter, from my understanding, how the cross-sectional area of the straw or of whatever container, all it matters on is the height. So we can't really exceed the 33 feet because
Mhm.
the atmospheric pressure is, it'll only press down so hard.
Mhm.
So, and water only has a fixed density because we can't really compress a fluid. So it'll always only go up that 33 feet.
Mhm.
So I don't think that it'll actually be able to go up the other 7 into our mouth. The other problem I think maybe is that well, like, how before the straw would have been filled with air. I don't quite know how the straw being filled with air before we start sucking it matters, like those extra 7 feet, how that affects the calculations and stuff. But I don't think it'll make it anyways.
Very good one. Yes. So you had talked about a key important factor in this, that what we're drinking is water. And we know that the atmosphere pressure could support 30 feet of water. And now you're trying to get it up more than that. So atmosphere pressure simply could not push it any further. The mechanism of us being able to drink our beverages from a straw, the mechanism of that, we always feel like, oh, it's me sucking the liquid into my mouth, right? That's how we feel, but it's not really us doing the work. By sucking, what you're really doing, you're just removing air that's in the straw. So you created a good enough vacuum. You suck the air in so that it's allowing the outside atmosphere to push the liquid into the straw, and then it got into your mouth. So it's not about you physically exerted a force on the liquid to get it in. It's the atmosphere doing the work. And you can see that, yes, you can create a 40 feet long vacuum in the straw, but the atmosphere pressure can only push up the water to a point of 33 feet. And at that point, the whole thing had reached a static equilibrium. The weight of the water column would satisfy, would cancel out the pressure of the, so the weight of the water at this point will be equal to the force from the atmosphere pressure, which is P naught times the cross section of the area. So when these two forces are equal, they're just not gonna go anywhere. So no matter how hard you try, we cannot drink from that height. The highest you will be able to do this is at 33 feet. Okay, very good. Okay, 1 second. So for the next one, I want to show the process by animating my slide. So let me go ahead and switch to my computer to show this. I'll have to switch back and forth. So one allow me to write and the other allow me to show the animation. Okay. So the next slides I want to show is Pascal's law. Pascal's law is saying that a pressure change at one point in the liquid will appear everywhere throughout the liquid. So remember we had talked about, okay, if you put a large pool and in the pool you put a ship on top of one point. So as a result of that, everywhere in that pool you're going to feel a increased pressure, not just the point that is right below where your ship was. So that was Pascal's law. So for example, if we have this sort of a U-shaped container, right now you filled it with water, okay? Right at the top, you have just atmosphere pressure P naught, and right at the bottom, you have that P naught. On top of that, you have rho GD, that is the added pressure due to the liquid with a height of distance d. So everywhere at the bottom, you have the same pressure. Everywhere at the top, you have the same pressure. So what if you put more pressure on one side? Right? So let's say you had applied a force on this piston of area A. So you're increasing the pressure on the left-hand side. Okay, so you might wonder, oh, am I only increasing pressure on the left? Pascal's law will say that this increase will appear at anywhere inside the fluid. Because when you pressure down on the left-hand side, you're squeezing some of the water to go up higher on the right-hand side. So eventually at the bottom, you're still looking at the left-hand side of the bottom and right-hand side of the bottom of the same pressure. So in terms of mathematics, it works out like this. Okay, at the top, we still have P naught. Right here on the surface of the left-hand side, you have P naught plus this extra force divided by the area that is added. Okay, right, on the right-hand side, you do not have such a force. And on the bottom of the left-hand side, your pressure will be whatever you had previously, P naught plus F over A, and that extra depth of water, that's rho G D1. And you can see on the right-hand side, the only difference is between their water level of the surfaces. So even though the right-hand side, even though there isn't a force applied on it, it has this extra height of water. So that extra height is exactly giving you the same pressure as the force gives you, because it's going to go up high exactly to a point that is equal to how much the force, the pressure brought by the force. So on the right-hand side, you have a total distance D2, which is bigger than D1. And on the bottom, you have atmosphere pressure plus the pressure of the water with D2. So these two will be equal. Okay, so so Pascal's law, because of Pascal's law, you don't have to worry about a particular force applied at one location of your liquid, but not the other. All you care about is at the same depth throughout a connected container, the pressure will always be the same. Okay, so let's look. Sorry, go ahead.
Right. So the right side of the container stays at the same original height.
Oh, it went up high. You can see the original height is like this. Let me show you the animation again. It was like this. And as pressure down, the right-hand side moved up.
Could you move it back to the original position?
Yeah.
Thanks. Sorry, the change was so minor that I didn't even notice it. Sorry.
Yeah.
Thank you.
Okay, no problem. All right, so now let's look at a question that is related to this. Very similar to what we had before. The difference is now we are adding forces on both sides of the container. One side, you added a person. Okay, so it's the weight of the person adding some extra force on the left-hand side. The right-hand side, you added a car, so it's much more force added. However, you can see that right now, the water level are exactly the same height. Okay, so the water level, the left-hand side, the right-hand side are the same. So that means, okay, despite that the force being different, the extra pressure you added must be the same. Otherwise, you will end up with one side of the liquid higher than the other. Okay, so can you, would you be able to answer the different surface area on the left-hand side versus the right-hand side? How much bigger is the area in the piston under the SUV compared to the one under the person? Recall that the pressure is related to both of the force and the area, right? P pressure is force divided by area. All right, so I'm going to open up the pool for you. If you want to take a moment, you can take a moment, and whenever you're ready, you can vote. So the added pressure must be the same. And we had talked about how pressure is force over area. And the force is obviously not the same, right? One of them is 60 kilos, the other one is 6,000 kilos. So one of them has 100 times of the mass than the other, so consequently the weight will be that much more. So think about how the area has to be related in order for the pressure to work out to be the same. We will wait for another 10 seconds and then we can wrap this up. All right, any last minute vote? Any more votes coming in? All right, so let me go ahead and end this. We'll take a look. Yes, okay, very good. The answer is the intuitively 100 times you have this ratio, and in turn out that ratio is a ratio we're looking for. So this is a ratio about their different masses. And that is the ratio for their force, for the weight. And the area has to be 100 times 1 versus 100, that same ratio, in order to make sure the pressure they added is the same pressure. Okay, so let's take a look at the calculation. If I'm drawing a dotted line right here at the surface of both left and right hand side, I see that they're at the same height, right? At that point, they have the same pressure, and that pressure is the atmosphere pressure plus whatever extra force you have added divided by the area that the force is exerted on. The force is provided by the weight of the person, which is on the left-hand side. On the right-hand side, the force is provided by the weight of the SUV. Now, setting these two to be equal, you can see that force times on the left times the area on the right is equal to force on the right times the area on the left. So this is just that relationship of that ratio. So your area has to be 100 times of the left-hand side in order to distribute that bigger force to make sure that you are actually given the same pressure. So this is showing again that your pressure is related to both force and the area. All right. Now let's move on to Archimedes' principle, which is a very important concept when we are looking at the static fluids. You have already done a lab, so you're not, must be familiar to you. Archimedes' principle simply states when you submerge partially or fully submerge a object in the fluid, then this object will feel a upward force try to support the object, buoyant force, that is equal to the weight of the fluid that is being displaced. And we call this kind of force the buoyant force. And you can calculate it by looking at the weight of the fluid that has been displaced. So the very important thing here, you need to use the density for the fluid. So if you put something in water, you need to use the density of the water, because we're saying this force is equal to the weight of the displaced water. So you have to use the density of the water, but not use the density of the object. If you use density of the object, then you're looking at the weight of the object, of the volume of the object, of that particular volume. Okay, so the rho of the fluid times rho times V give you the mass times G give you the weight of the water. Okay, so the volume of the fluid is how much fluid has to go away, meaning being displaced, in order to make space for the stuff you put in. So if you put a cube and put it inside the water, the same volume as your cube, same volume of water has to be displaced. If you put a cube halfway into the water, then half of that much volume has to be displaced in order to make space for the object. Okay, now if you partially submerge it, the volume of the displaced fluid would be less than the entire volume of the object. So let's look at an example showing different scenarios, right? So we have done, this is similar to our lab where we're weighing objects in air versus in water. So if you look at the first picture, you're just putting an object and weigh it in air. Well, we know how much weight we will measure. It's just going to be the weight of that object, right? But on the for the other two, we know that the measured weight will be less, because when you put it in liquid, either fully or partially, the liquid will provide a supporting force. So just instead of the water, think about someone is using their hand to support it a little bit up, up, then you're going to measure a smaller number. So the exact number that you measure will be the original weight minus whatever extra support you're getting. That difference will be what you measure. So let's look at the calculation for each one of them. Here we're looking at a cube of iron. We can calculate the mass of that iron using density times volume. Density is given in kilograms per centimeter cube, and the volume is simply the volume for this 2 to the power 3, 8 centimeter cube. So I have 64 grams. You can convert that to kilograms. When it's out of the water, the measured weight, so how much force you're pulling up is equal to the weight. That's simply, this tension is going to equal to the weight. So mass times little g, mass times gravitational acceleration. Okay, so that's how much you will measure if you put it in air. But if you put it in water, then other than the tension, the gravity, you have an extra supporting force from the liquid, that's the buoying force. So whatever you're measuring is going to be the difference between its weight versus the buoyant minus the buoying force. So mg minus F of B. Now F of B will be different, right? Whether you put it fully in water versus halfway in water, you're going to get a different F of B. If you put it fully in water, the displaced volume is bigger than the displaced volume if you put it only halfway, right? So if you put it fully in water, the buoying force is going to be rho, density of the water, times the volume of the entire cube, which is 8 centimeter cube times g. And then you can calculate your tension in that case. The difference between 0.64 newtons and 0.08 newtons and give you 0.56 newtons. If you put it halfway in the water, everything is the same, except F of B is now half of what you had, because you're only putting it halfway. You're displacing half of the water as you had before. So the measured weight will be slightly more than you measured if you put it fully in the water. Okay, so I'm sure this calculation doesn't look too hard, given that you have already done a lab that's very similar to this. So you have this question. I think this is a really, really good question. Let's think about this together. You had a bridge question where we have a glass of water and we put an ice cube in it. It's floating, right? We know that the density of the ice cube, how does the density of an ice cube compare with the density of water? What do you think?
I think they're about 90%. So the density of the ice cube is less, and it's about 90% as much as that of the water.
Very good. Yes, the ice cube has slightly smaller density than the water, so it floats in water. And we also know that as a consequence of that, if your density is smaller, if you have this much water, let's say you have how many mass? 2 kilograms of water. Okay, now if you put that in the freezer and make it become ice, then since its density had changed to be smaller to have a mass to be conserved, mass conservation, that 2 kilograms has now to be a little bit bigger than before. So if your density decrease, your volume has to increase. So that's why when we sometimes fill our container with water and then freeze it, we have to be a little bit careful. We know that the ice will expand, and we have to think about give it a little room, extra room for that. Well, that's on a side discussion. But anyway, we put an ice cube floating in the water, and eventually the ice cube melts. So let's say you made a little mark on your level of the surface of the water. And then once it melts, you look at that level of the water again. What do you think? What do you think about the level of water? Do you think the water level rises up or falls down? Or would it stay the same? Any thoughts?
Wouldn't it stay the same?
Okay. And why is that?
Isn't it because as the ice is melting, well, the ice itself is already like, it's like a tiny bit above the water because it's less dense.
Mhm.
But at the same time, when it's melting, it'll become less voluminous or whatever because it's less dense than the water and it's more, the molecules are more separated. So
Mhm.
as it melts, even though like you're getting more water in the container, you're like making like the volume of ice that you're losing is, you're like losing more ice than water, and you have a little bit, the ice is a little bit above the surface, so it just makes it so eventually it's level.
Yeah, very good, Grant. That's exactly correct. Even though that your ice cube right now has a little bit that's on top of the water. So when it melts, it's not really just what's below the water is now being replaced with water, because water now has more density, which means it occupies less space. So it's okay that your ice cube is a little bit bigger than what it occupies, because when it becomes water, it doesn't need to occupy as much of a space. So it will all just be filled in with that volume that eventually just being displaced. Very good. So your water level will not change and it will remain the same. So if we walk through that reasoning process, again, we will say, well, because the buoyant force is always equal to the weight of the liquid being displaced. And at this point, your ice cube is floating, which means the ice cube is at static equilibrium. The weight of the ice cube is equal. So there's like a step in between. So the ice cube is the static equilibrium, which means the weight of the ice cube is equal to the buoyant force. But Archimedes' principle saying the buoyant force is also equal to the weight of the water displaced. So connecting these two equations, then you get the weight of the ice cube equal to the weight of the water it is being displaced. So you see that little extra bridge in between them. And that's important that when your ice cube now melts, it becomes water with the same weight because, well, you had let's say 2 grams of ice cube, and that's the mass. Then we are saying that it's going to still become 2 grams, obviously. It's not going to change its weight. And it was occupying and displacing 2 grams of water. So you just have just enough space for the ice cube to go. And it will simply just take place of the water and the water level will not change. So if we look at just water displacement, it's probably a little more easy to visualize if you're filled your tub with water, right? Because now you can clearly see how much water is being displaced. So for example, you have a tub of water that's filled all the way up to the brim, and then you throw in a ship. So because to make space for the ship, some of the water has to be displaced. Now you can see it clearly is out of your container. Now you're wondering, well, do you think which one do you think I have changed the weight of this entire thing by putting a ship on top? Well, which one weighs more? Do you think the one that filled with water only or the one with water and ship together? or will they weigh the same?
I think that, or,
Oh, go
oh,
ahead.
oh,
Do you have
sorry, I
some?
wasn't sure if it was like one where you wanted us to,
Oh, I was going to go ahead and open up the pool.
oh,
We'll do a quick poll then. All right, I will, let's run for another 10 seconds to wrap up. All right, any last minute vote? Okay, so let's go ahead and stop and take a look. All right, so a majority of you guys have voted for they weigh the same. So looks like the only difference between these two is one of them has the ship, added a ship, but lost some of the water, right? So if we think that they weigh the same, what we are claiming is the water that you spilled that's been displaced as a spilled water is exactly equal to the weight of the ship. So how can we justify that the weight of the ship is equal to the spilled water? So how do we justify that? Anybody like to share some thoughts?
so how I figured it out was that in the picture, we see that the battleship is not touching the bottom of the container.
Mhm.
And we also see that the tub of the water, it stays this. I'm going to assume it didn't magically change dimensions. So then because of that, the water appears to be at the very top in both cases.
Mhm.
So that means that overall they have to have the same weight, because since the battleship doesn't touch the bottom, we know that the water displaced is greater. I mean, sorry, the weight of the water displaced is equal to the weight of the battleship, right?
Mhm.
So then that water displaced would have been the water that was another tub that's now on the floor. So that's how I got that they ended up being the same.
Very good. The important thing to notice that, yes, you need your battleship to not touch the bottom, because that will give us a equilibrium condition. So you can relate, you can say the weight of the battleship is equal to the buoyant force that the battleship is feeling. That's one equation, right? And then you use Archimedes' principle that relate to the buoyant force is equal to the water being displaced. That's the water on the floor. That's the water that you spilled. Because of that also equals, and then you can relate to the weight of the battleship to equal to the water displaced. So through that sort of chain of reasoning, we have figured out that yes, they will weigh the same amount. This is also a bridge question. I think we should be easy to answer at this point. If we put our ice cube in water, we notice 90% is underneath the surface, which makes sense because we know that the density is about 90% of the density of the water. Now, if we put same ice cube, but instead of putting in the water, we put in something else, like a liquid that has less density than the water. So would the ice cube be submerged more or less? Now we know that you need to provide the same kind of buoying force than before, right? To support the weight of the ice cube. So the buoying force is rho GV. You need the density of the liquid times the volume of the displaced liquid times little g. Now, if you put it in a liquid that's less dense with a little rho, smaller rho, then your V has to go up. Then you need to displace more of that liquid in order to provide the same amount of buoying force. So which means that you simply need to be submerged for not more than 90%. You need a bigger volume. So if you put it in alcohol, for example, then you would displace more alcohol, which means your ice cube will be sinking down a little bit more than 90%. Okay. In terms of Archimedes' principle, there is a very well-known and popular story. It's also very interesting. I'm not a historian, so I cannot vouch for the validity of all the details of that story, but the general story goes like this. So Archimedes was given a task by the king. The task is very hard. The king made a golden crown, asked someone to make a golden crown. Let's say they have some pure gold, and he gave it to a goldsmith and make a crown out of it. And the crown was made and was also the same weight as the original gold that was given. But the king suspected maybe some silver has been mixed into the crown. So, but we cannot break up the crown and then it weighs the same. How can we find out? So he tasked Archimedes to figure that out. So it's just thinking about this question really hard. And one day while taking a bath, notice, oh, as I step into the bath, the water is being displaced. And that gave him an inspiration to figure out a solution to this problem. I got really excited. So he didn't even put clothes on. He ran outside, say, I found it, I found it. I found the solution. So what is the solution that he found? So he found out that what we can do is, all right, we can put the crown and another volume, some kind of pure gold, and we just say, okay, let's use the same kind of weight of these two different, the crown or the pure gold, and then they're balanced in air. Now let's put both of them in water to see if they're still balanced. If they're still balanced, meaning that they have the same density, the crown is not being mixed with silver. But if one side goes down, in this case, only one side could go down, is the gold. If the crown is less than the gold, so if the crown had some silver that's been mixed in, then make the overall crown has a smaller density, right? Because silver has less density than gold. So if you mix some silver in, you're lowering the overall density of your crown. So which means then overall you will, with the same amount of volume, you would have a bigger volume. Okay, so if you have same amount of 2 kilograms of some object, but if you're saying 2 kilograms of iron versus 2 kilograms of cotton, which one is bigger? Now, obviously the cotton, you need way bigger volume in order to also have 2 kilograms, right? So if the crown has been mixed with some silver, then crown would have a bigger volume than pure gold. So that volume will show up when you put it in water because they will displace that much volume of water. And as a result of that, they will feel a different kind of buoyant force. The one with a bigger volume, in this case, is the crown, will have a bigger buoyant force. The buoyant force is rho g times v, right? The volume that you displace, than the gold. So the gold will feel smaller f of b, the buoyant force, and the gold will go down a little bit more. And the weight is, the scale is no longer balanced. So they did this testing and turned out indeed the crown does have a smaller density, so it's not no longer pure gold. So he figured out the solution, and he also came up with Archimedes' principle, the one that we just learned. Okay. Okay, sorry, that was just one extra slide. Let me take a look at how much time we have left at this point. So if we have time to look at this following of the questions. All right, so we will continue. Hopefully we can do, if not all, but part of this question. So we can conclude our discussion on static fluids. So here we have a U-shaped tube and you fill it with water and also oil. The blue are the water, the yellow on the right-hand side, that section is oil. We know that oil is has less density than the water, right? So when you mix water and oil, the oil will always stay on top because it has a smaller density. So it reached a static equilibrium like the picture shown here. You have a height H1, 33 centimeters on the left-hand side, and the right-hand side, you have some water, H2, 12 centimeters. On top of that, you have another H3, 31 centimeters of oil. And we know that atmosphere pressure is the standard given quantity. And we know the density of the water. So the first question is, what is the absolute pressure in the water at the bottom of the tube? Okay. So we can see that if we're looking at, if we're curious about the pressure at the bottom of the tube, it doesn't really matter if you calculate it using the left-hand side or the right-hand side, because the whole thing is in the static equilibrium, right? So to calculate the pressure at the bottom, PB at the bottom, we can, it is an easier calculation if we simply say, okay, so look at the left-hand side of the bottom, you have atmosphere pressure, and on top of that, you have a column of water, which is height of H1, 38 centimeters. Okay. So we can simply say the pressure at the bottom is the pressure of the atmosphere plus density of the water times G times H1. So I'm using the left-hand side to do this calculation. It doesn't matter if I use left-hand side or the right-hand side, because they're going to give you the same result, because it's both at the bottom. And the second question is, what is the pressure at the water oil interface? So PI, P at the interface. Well, how do we calculate that? We realize, okay, now if we know the bottom, how much pressure is at the bottom, and now you're looking at a little bit above that with a total difference in height of H2, right? So we know that the pressure at the interface will just be smaller than the pressure at the bottom. And the difference is really just rho GH2, the density of the water times G times the height of H2, right? So that will allow us to calculate the pressure at the interface. We use the pressure at the bottom, which was from the first question, minus rho water times G times H2. Okay. Third question is, what is the density of the oil? So we kind of go backwards to see that, well, the reason we didn't choose to calculate our pressure at the bottom using the right-hand side of the column, simply because we are not given the density of the oil. So we can backtrack and now figure out what the density of the oil is. The density of the oil is different. So whatever that density is, you're able to write down an equation relating P at the interface is equal to the pressure of the atmosphere plus whatever extra density is brought on by that extra column of oil. So we can say, well, PI and P atmosphere, the difference between that pressure is simply the extra added column of the oil, is density of the oil times G times H3. So that allows you to calculate the density of the oil. All right, so this is really just an exercise, repeatedly using the hydrostatic pressure of a liquid underneath the surface of a liquid is rho of that liquid times g times the height of the liquid. If you are at a height h below that liquid, you're feeling a pressure that is whatever in the atmosphere and whatever rho gh is. So you need to add these two together. So this is just a question that use that relationship over and over again, whether it's for water or is it for oil. All right, so we've been talking about static fluids. When we meet on Friday, we will conclude all of our discussion to look at fluid flow and fluid dynamics. So I know that we kind of went through this kind of quick. You will have a chance to do with this in engineering if that is your field, but that's all the time we have to do it in 1510. But don't worry that our exams for this particular type of topic will not be too difficult. It will just be sort of a very about on the same kind of difficulty as what we did in class. So mostly conceptual. If you know the concepts we talked about, you should be okay with these tests. All right, I'm sorry I went over a few more minutes. I will see you guys on Friday. Bye, everyone.
Bye, Professor. Thank you. Have a good day. See you Friday.
Have a good day yourself. Bye, everyone.